Well, good morning, everyone. Welcome to Cosmic Coffee. I'm Jeff Hall, an astronomer and director of the observatory here in Flagstaff. Welcome again to an episode where we try to cover topics on all things astronomical, live streaming to you while we're all kind of stuck at home. As usual on Cosmic Coffee, we give a little shout out to a local business, so locals might be inspired to go give them a little support. This morning, it's Wicked AZ, our technical director behind the scenes here, Danielle Adams, I think reliably goes there on her way to work. And so go by and give our local businesses a bit of support. Today, we're joined by Dave Sawyer, who's our technical project manager here at Lowell Observatory. Dave right now is in charge of managing and moving the whole Astronomy Discovery Center project forward, which is a non-trivial task, but he also has another Lowell connection in that before he came here, he was involved with building the EXPRES spectrograph now at the Lowell Discovery Telescope. And we're going to talk a little bit today. We've heard in previous episodes of Cosmic Coffee about some of the science of finding Earth-like planets around sun-like stars. And we thought today we'd go to a different level or aspect of the problem and talk a little bit about how do you construct the kind of instrument that's capable of teasing out these teensy little signals in the data? And that's what Dave was in charge of before he came here to Lowell, and was a really good catch, and we're glad to have him here. So welcome, Dave.
Thank you very much, Jeff. Glad to be here. Yeah, this is, kind of fun because it's going back a few years. And like Jeff said, before this, I was at Yale University, where we researched a lot of the technologies associated with searching for exoplanets and developing instruments for that purpose. And so building this next generation instrument for the Lowell Discovery Telescope was exciting, and I'm looking forward to talking about it. So I thought I would just start, I'm sure everybody knows what an exoplanet is, but it's basically a planet that orbits a star other than our sun. And then an exo-Earth happens to be an Earth-like planet orbiting a star other than our sun. And so I'm going to first talk a little bit about why we do this, and then focus more on the technical aspects of building an instrument to actually be able to detect an Earth-like planet around another star. So I thought I would start with hold on, I'm not advancing. What makes a planet Earth-like? And basically, an Earth-like planet is a rocky planet that can maintain liquid water on its surface. And in this diagram I'm showing, the left vertical axis is showing stars of different sizes, going from one solar mass to two solar masses and then smaller. And then on the horizontal axis is the radius of the orbiting planet. And what's shown here are the planets in our solar system. And here's Earth at 1 AU with one solar mass sun. And the Earth is the only planet in the habitable zone of our solar system. And then as you get to larger stars, the habitable zone moves farther out because the stars are hotter, and having liquid water is not possible closer to the star. And then moving to smaller stars, you can get closer. And this is kind of important, and I'll talk about this later, because we're actually measuring the influence of the planets on the stars, and smaller stars have more influence from the planets. So why do we do this? This is a question that's been haunting mankind since we started looking at the sky. In fact, there are writings from the Greek atomists at 5th century BC talking about infinite worlds. And we really started looking at this in earnest, developing the search for extraterrestrial intelligence program, which started in the 60s, looking for radio signals that might be from an intelligent civilization elsewhere. Then in 2009, we launched the Kepler Space Telescope, which over its 10-year program discovered thousands of exoplanets. And then Curiosity rover has been scouring the Martian surface since late 2012, searching for evidence of microbial life on the surface of Mars. And then finally, the topic of this talk is the EXPRES instrument, which was installed in 2017 and started observing in 2018 at the Lowell Discovery Telescope. So the couple of advantages of EXPRES over Kepler are the EXPRES can survey more of the sky, and so look for more potential candidates. Plus, it uses a different technique that does not require planets to transit in front of the stars. And because it uses a different technique, which is spectroscopy, we can actually learn some of the physical properties of the stars.
And I'd say one other thing, Dave, if something with EXPRES breaks, it's also a little easier to get to.
Yes, indeed. Okay, so talking about the chance of life, many of you have probably heard of the famous Drake equation. Dr. Frank Drake produced this probabilistic argument to determine what the likelihood of intelligent civilization elsewhere was. And this was presented in 1961 at, I believe, the very first meeting of the SETI program. And so I'll explain what the equation is. And so basically it's determining the number of civilizations in our galaxy with which communication might be possible. And so that's calculated by determining the average rate of star formation in our galaxy times the fraction of stars that have planets, and of those planets, how many are in the habitable zone, and then what is the fraction of the habitable zone planets that life actually evolves, and of that, what is the fraction that evolves into intelligent life? And I know what that means is controversial, but basically intelligent life here is defined as a species that could actually learn to communicate. And then that's multiplied, well, actually I jumped ahead. So the intelligent, and then of the intelligent life, the fraction that can develop the technology to communicate, and then multiplied by the length of time that the civilization exists. And so the first two of those, the rate of star formation and the fraction of stars that have planets, is pretty well known from astronomy these days. This talk and what current science is trying to do is determine what the number of habitable zone planets is. And then the factors below that are all pretty well unknown. There's numbers that can be guessed to put in those, but if you put in all the different numbers that you could possibly have, the number of civilizations comes out to either be infinitesimally small or astronomically large. So really, we don't know.
And we don't know, but I remember Carl Sagan covering all of this in the original Cosmos series and pointing out the importance of that last one. You know, once a society becomes intelligent and communicates, how long does it last? Does it last a long time, or does it wipe itself out after 50 years for whatever reason. And that turned out to be a big factor.
Yes, for sure. Yeah, I think the numbers that are estimated for that are from 1,000 years to 100 million, somewhere in that range.
Yeah, typical astronomical accuracy, right?
Right. Okay, so then now I'm going to just quickly talk about the ways of finding exoplanets before we get into the instrument itself. So one way is astrometry, which basically is watching the star move across the sky and looking for wiggles. It basically creates a sine wave kind of shape as it moves across the sky. As you can imagine, that requires a very large motion and a very close star. Because of that, there's only been one planet discovered this way. And I should add that these numbers may have changed since I put this slide together. So I would just use them as, relative numbers. Direct imaging is being able to actually physically image a planet around another star. There have been 50 of those discovered. Gravitational lensing is another technique that I'm not really that familiar with. And there have been 96 discovered using that technique. And then more commonly, the transiting method, which is the method that was used by the Kepler project and TESS, which is currently, was recently launched and is currently observing, uses the transit method. And here in this diagram, shows that in this plot is the brightness versus time of a star. And as a planet transits in front of the star, it blocks a little bit of the light. And so you get a slight dip in the light curve caused by the planet passing in front of the star. Now, in this case, it shows the planet as a black dot. In reality, you would not be able to see the planet transiting in front of the star. You would only see the dip. And so this method requires that the planet basically be orbiting edge-on so that it passes in front of the star, and also that it be relatively large. Otherwise, the dips would be so small that we wouldn't even be able to detect them. And then finally, the topic of this talk in instrument is the radial velocity or Doppler technique. And so far there have been, for the transiting, there's about 3,200 planets discovered, and the radial velocity technique is about 810.
And of course, it's Kepler principally responsible for that very large number in the transiting that really revolutionized our understanding of just how full of planets our galaxy actually is. Before we go on, a very quick question from Will Carter. Just wondering what schools you went to, Dave.
Oh, well, so I got a bachelor's degree in electrical engineering at Wentworth Institute of Technology in Boston. And then I got a master's degree in astronomy at San Diego State University. Okay. So then moving on, I just wanted to, I mentioned spectroscopy because the radial velocity method requires spectroscopy, and I thought I'd just do a quick spectroscopy primer for anybody that might not understand exactly what that is. So basically, spectroscopy is the method of taking light and spreading it out as a function of wavelength. And so white light, like the light from the sun, if you were to spread it out like through a prism, you would create a spectrum. So for example, a rainbow is a spectrum of the sun, which is produced by water droplets that act like prisms. And so in this diagram, if we look at a star and take the light and pass it through a prism, it creates what's called a continuous spectrum, where it breaks out the light into all its different wavelengths. And since white light contains all wavelengths, it's just a continuous spectrum of the different colors. If there's a cloud of gas in the way, which with stars there is because their outer atmospheres are gaseous, Then if we create a spectrum of that, we see these dark lines where certain energies have been absorbed by the gas, and the light is basically removed from the continuous spectrum. And then lastly, if we were to look at the cloud of gas and not the star, we would see emission lines where that energy that was absorbed by the cloud of gas is re-emitted as emission lines. And so for radio velocity measurements, we're looking at the stars, and so we're seeing these absorption lines in the spectrum. And I'll talk about how we actually extract that information next. So here, this is an illustration which I'll show an animation of, but in this case, the large sphere is the planet, and the small sphere is the star. And because they're orbiting around each other, basically they orbit around a center of mass. And so it's not the planet orbiting around the star, it's the planet and the star orbiting around a center of mass. So as the planet moves around the star, it creates a wiggle in the star. So this illustration shows how the planet and the star move around. Now, if we were observing that from this vantage point here, you can see as the star moves toward us, the spectrum moves toward the blue. As the star moves away, the spectrum moves toward the red. And so basically, we're trying to measure that motion of the absorption lines to find the planets. However, the Doppler shift from an Earth-like planet is very small. In fact, the motion created by the Earth on the sun is about 10 centimeters per second, closer to 9 centimeters per second. That's pretty slow. It would take a minute to cross a large room at 10 centimeters per second. In fact, it's about the speed of a walking tortoise. However, when we're measuring the spectra of stars, there are a lot of other influences from the star itself, which I'll talk a little bit about, but these influences can be very large. And so what we're trying to do is measure the speed of a walking tortoise who's walking among a stampeding herd of buffalo. Now, some of those influences I'll talk about here. So now I'm getting more into the technical aspect of this, is the challenges of getting to 10 centimeter per second precision, being able to measure that tortoise speed. So first of all, instrument precision and stability, which is what this talk is primarily about. And then I just wanted to mention these astrophysical effects that also influence that we have to take into account when trying to discover the exo-Earths. So there's the boiling motion of the star's surface, and this boiling motion, where the gases come up from below and pop out at the surface, are measured in kilometers per second. We're trying to measure centimeters per second, and so that's a big source of noise in the data. There could be features on the star's surface, such as sunspots and plages, which create dark areas which affect the line positions. And so, it can be hard sometimes to determine whether it's a sunspot or something else that's causing a line to move. Then there's the motion of the Earth. The Earth is rotating. It's orbiting around the sun. And the sun itself is moving relative to whatever star the exoplanet might be around. All of these motions are affecting the measurements of these lines in the spectrum. And then closer to home, there's the Earth's atmosphere, which causes turbulence as the light comes through it. That's what causes stars to twinkle. And that causes the images to move, which is a unstable illumination, which also causes lines to move around in a spectrograph. So we need to count for that. And then finally, there are these molecular lines in there are molecules in the Earth's atmosphere that absorb light, such as water and oxygen, but they're variable depending on the temperature of the atmosphere, the thickness, the pressure. A lot of things affect those lines, and so they're constantly changing. And since these same lines are being absorbed in the stars we're looking at, then the changes in the lines here have an influence on those, and that affects the measurements. So as I said, I just wanted to mention those. I'm not going to talk about them here. I think each one is probably a talk in itself.
It certainly is.
I'm just going to talk about getting the instrument precision and stability that's required to measure 10 centimeter per second. So this is just to introduce, Jeff already did, the instrument itself. On the left is a picture of the 4.3 meter Lowell Discovery Telescope, located near Flagstaff here in Happy Jack. This instrument is installed on that telescope currently. The picture on the right is a picture of the instrument itself, or at least part of the instrument, which is located in the basement where things are more stable. And I'll explain that in just a minute. So EXPRES, as I mentioned, was designed and built at Yale University, and it was installed in the fall of 2017, and it's been in operation now since 2018. So this is a little cartoon to just introduce the parts of the instrument, and I'm going to go into a little more detail of certain aspects of the instrument that are, kind of novel and interesting. I'm by no means going to talk about all aspects of the instrument, but so anyway, on the left is the telescope itself, which primary function is to take the light from the object you're looking at and focus it to a point. And so that's this green arrow coming in to this part of the EXPRES instrument that's called the front end module. If I say FEM, that's what I mean. It's, an acronym we've been using so long, it's hard to get away from, but it's the front end module that collects the light from the telescope and focuses it onto a fiber optic cable that then runs 60 meters down from the telescope into the basement into a environmentally controlled spectrograph room, and the part of the spectrograph that's called what we call the back end module, the business end of the instrument. And I'm going to look at specific components of this, and I'm going to start with very high resolution, because to see the motions of these lines, very high resolution is essential, because the motion caused by 10 centimeters per second has a magnitude of about 1.5 nanometers. Human hair is about 100,000 nanometers. And so it's very tiny. In fact, it's, 1/10,000th the size of the pixels in the detector that we're measuring these with. So high resolution requires a type of spectrograph that's called an Echelle spectrograph, which has a unique kind of grating that spreads out the light into very, very high resolution. But because of that, it has to stack different orders on top of each other, because the spectrum just would be so long and huge if you didn't. And because of that, then the light has to pass through prisms and be dispersed in the direction to separate those orders that are all stacked up on top of each other. And then there are other components such as collimators and optics and a camera. And so specifically, if we look at the EXPRES instrument, light from the fiber comes in here, it gets collimated and then bounces off of the shell grating. Then the collimator acts as a focuser then for the light, which bounces off a specialty kind of mirror that corrects for some aberrations, gets collimated again before passing through the cross-dispersing prisms, and then passes through optics and finally into the detector here. So some of these components, making these components is quite difficult because to get this resolution, they become very large. The cross-dispersing prisms that are in EXPRES are shown here. At the bottom, you can see a 12-inch long ruler. So very large, beautiful pieces of glass. The grating itself is about 3 feet long, weighs a couple of 100 pounds. And like I said, the parts get very big to do this. And then finally, what these produce is a spectrum that looks like this. So each one of these lines is what we call an order. They're individual spectra, and the grating produces the dispersion this way. All these little dark spots are the absorption lines in this star, and then the cross-dispersing prisms create the separation in the Y direction so that we can separate all these different orders. And so blue wavelengths are here all the way to red wavelengths, but this is a continuous spectrum of the star 51 Peg, which happens to be the very first exoplanet discovered using the radial velocity technique. And like I said, these are the absorption lines in 51 Peg that we actually measure the motions of. So next, I'm going to talk about the uniform illumination. I mentioned that a little bit before. Very important because if the light coming into the spectrograph is wiggling, then the lines that it produces are going to wiggle. And since we're trying to measure teeny tiny wiggles, those are very undesirable. So there's a variety of things we do to stabilize the illumination. First, we stabilize the image coming in. I'll talk about that using a fast tip tilt mirror. Then we use octagonal fibers and a double scrambling technique to get rid of modal noise that's created by the fibers. And then finally, we do an agitation, which further removes any noise in the system. And I'll talk about each of those individually. First of all, the tip tilt correction. This is an image of the actual instrument that's mounted, the front end module that's mounted on the telescope itself. And this is where the light is connected and injected into the fiber. Here, this shows the optical path. The light comes in, gets redirected by a fold mirror to a collimator, which collimates the light and then reflects off another mirror that's attached to a high-speed motor, a piezoelectric motor, that allows this mirror to wiggle. And then that light gets focused to the fiber feed. This is the fiber that actually runs to the instrument in the basement, the back-end module. And then light from that mirror also goes to a camera that allows us to look at the star, to see the star we're looking at and correct for image motion. So first, the fiber feed mirror. This is actually a picture of the fiber mirror. You can just make out somebody's fingers here. It's pretty small. That fiber is 66 microns, so roughly the size of a human hair. And so basically, we're taking all of the light collected by a 4.3 meter telescope and focusing it onto that fiber right there. Not all of the light gets in. some of the light spills over around that fiber, and that light is what we see at the camera, and it shows us what the star looks like. And because of atmospheric turbulence, this star image moves around. And so using this camera, we measure a centroid and then feed back a signal to this fast tip tilt mirror. So the red, this is showing offset in pixels of this camera here versus time. So basically in the X direction, that's up and down here, this is how much the star is moving as a function of time due to atmospheric turbulence. But then using a control system, we then feed back that signal to the fast tip tilt mirror, which exactly wiggles opposite the motion of the star coming in and then flattens it out. So for example, this green curve here is the corrected image, and that star image here that's a little bit distorted and wiggling, if we were seeing it real time, becomes very stable and round. And so we get very uniform illumination into the instrument with that fast tip tilt correction. Then moving on, once we get the light into the fiber, one of the an advantage of using a fiber-fed spectrograph is that the spectrograph can be located in a stable environment, not mounted on a moving telescope in an environment that's changing temperature, changing gravity vectors, all that. Here we can put the spectrograph in a very stable, controlled environment, but you have to feed it with a fiber. And fibers themselves introduce problems because they create modal noise, which is basically the light running through the fiber likes to take preferential paths. And so it gets, accumulated in some parts of the fiber and not others. And so you get like a speckle or a mottled appearance of the light coming out. And I'll talk a little bit more about that, but I wanted to show the process here. From the telescope down to the spectrograph room, we bring the signal down in an octagonal fiber. And an octagonal fiber has, it's just that. It's got an octagonal shape like a stop sign. And because it's not circular, it tends to break up the tendency for light to follow the same paths. And so you get less of the modal noise here. And then we also do a technique of double scrambling, which kind of reverses the images and also removes that noise created from fibers. And then at the same time, we do something novel, and that is we take the image of the octagonal fiber, which, as I mentioned, is 66 microns across, and that's what sets the resolution of the spectrograph. And we want high resolution, and so you have to reduce the width of that. And a lot of spectrographs use a technique called a slit, where you actually take a slit and block the light outside of the slit. It makes it narrower, and you improve your resolution. Here, this light signal is so important, we didn't want to do that. So instead, we take that image and we slice it and then re-image it onto another fiber that's rectangular. So we're taking an octagonal shape, cutting it in half, and re-imaging it onto a rectangular fiber. So now that the resolution has doubled, but none of the light has been lost in doing that. So the modal noise I mentioned, shown here on the right, this is a circular fiber, this is an octagonal fiber, and you can see inherently the modal noise is a little bit less in the octagonal than the circular and the rectangular. And so even with the octagonal, there still is this modal noise, which is undesirable. And if you move the fiber, these little spots move around, and that affects the image. So ideally, you want to move them around so that they all smear out and eliminate those. And so we use a technique called agitation for that. And we did a lot of research on what the right amount of agitation, the speed, the magnitude, the best technique. And it was found that the best and it has to be random to eliminate, any symmetry in the scrambling. So we found that the best way is for a human to physically hold the fiber in their hand and just wiggle it, because it's going to be random. It's about the right magnitude to do that, and we found that worked the best. But we did be a little boring sitting there all night shaking a fiber, so we built a scrambler with two arms, which you can see here running in the video. And the two arms run at different speeds so that they create some chaotic motion, and the magnitude is about the same as shaking it by hand. And what that does is it takes the modal noise you can see on the right and smooths it all out to what's shown in the orange there, and that's what's injected into the spectrograph. So we get a very uniform, stable light source coming in to the spectrograph. And then finally, not finally, second to last, environmental stability is very important, and there are many aspects here. That we have an environmentally stabilized spectrograph room that the spectrograph is in. It's inside a vacuum chamber, and we have controls for thermal and pressure. And I'll talk about those. So this is the spectrograph itself I showed earlier, and it's mounted inside a vacuum chamber, which is maintained at a very high vacuum so that any changes in pressure, like atmospheric pressure, have no effect on the instrument itself. And then for a vibration isolation, this instrument is mounted on an isolated slab, a slab where basically the floor of the observatory was cut out and a new pier was put in down to bedrock, and then a gap was left between it and the building. So any vibration from wind on the telescope building, or even the telescope, the dome rotating, things like that, don't get transmitted to the instrument. And then it is sitting on isolation springs. The enclosure is, and then the instrument inside the enclosure is on another layer of isolation springs. So very well isolated from vibration. And then for thermal stability, the enclosure has radiation shields to minimize radiational cooling or heating. The instrument itself, this monocoque structure that it's mounted in, is made out of a material called Invar, which is very stable to temperature changes. And then finally, I'll show this whole thing is wrapped in a cocoon to stabilize it. But these plots show that the spec for the stability of the spectrograph room is shown here, plus or minus 0.5 degrees Celsius. And so this is showing a swing possibly, over the course of a day. And in the day, it gets warm by 0.5 degree. At night, it gets cool by 0.5 degree. And then through simulation, it's determined that the optical bench, which is this part here, is stable to less than 0.15 millikelvin. So that's 0.15 times 10 to the minus 3 Celsius. So very little change there in temperature, which means that all the optical components are very stable and nothing is moving around. And this shows the spectrograph enclosure wrapped in this thermal cocoon as another layer of thermal stabilization. And then the last thing I wanted to mention was wavelength calibration. There's a lot involved with calibrating the spectra, especially to get the precision that's needed. And I'm not going to talk, there are some novel aspects here as well for flat fielding and things like that. I'm not going to go into those, but did want to mention the laser frequency comb, which is an instrument that's used to calibrate the wavelength. And the laser frequency comb is this instrument here. It's built by a company in Germany called Menlo Systems. And the concept for this won the Nobel Prize in 2005. And basically, it produces a very stable spectrum because it's laser locked to an atomic transition. So the stability is something like in the 10 to the minus 12 range. And so the laser is mode locked, so it produces a series of discrete, equally spaced pulses. And then these pulses are, actually still very close together, so they have to be filtered like through 3 layers of filters to eliminate most of the pulses so that we can actually discern the individual pulses. Then somehow, magically, something called a photonic crystal fiber takes these pulses of laser light and converts it to pulses of light at different wavelengths over a large wavelength range, 400 nanometers to 750 nanometers, roughly. And that's what's shown here. This is a picture of the actual spectrum of the laser frequency comb spectrum. And so you get these pulses that are evenly spaced about every 10 pixels on our detector. And they're flattened so that they're the same intensity at every wavelength. So you get very high signal to noise for your wavelength calibration. And this basically is a reference because you pick any line here and to an accuracy of 10 to the minus 12 what wavelength that line is. And so then we can reference the spectrum obtained with the instrument to that and determine what the actual wavelengths of the absorption lines are. So this image here shows the science mode where we actually interleave an observation of a science object with an observation of a laser frequency comb spectrum, which is sent all the way up to the telescope, injected into the same fiber feed mirror. It follows the same exact light path as the science data and produces this spectrum. And so this is the science mode because it follows the same path as the science, which is desirable because it corrects for any variations in, the fiber running down from the telescope. If it moves a little bit or if the temperature is a little bit different in the observatory, it's corrected for. And then another mode, which I just wanted to put up for demonstration, is a mode called simultaneous, where along with a spectrum, which are these solid lines, if you look closely, you can actually see the absorption lines from the star. We can use a simultaneous fiber to simultaneously project the laser frequency comb juxtaposed to the spectrum. And that's what's shown here. This is more used for instrument performance tracking and things like that. And so finally, what this all comes down to is finding planets. And so on the left here, this is the data from the Elodie spectrograph, which was the spectrograph that was used to discover the first exoplanet using the radial velocity technique. Now this planet happens to have a very short period. It's only 3 to 4 days. So you could conceivably get a lot of data in a single night that would be continuous, but more typically, observations are taken over a long period of time to basically try to sample all the different parts of this curve. And then the data are overlaid depending on a phase, basically depending on the orbital period. If you can get a match from all the data that stacks all of the measurements into a sine wave like this, then that indicates the planet. And so this was the actual discovery of 51 Peg with the LED spectrograph. And then on the right is the same data taken with the EXPRES instrument. And you can see, looking at the error bars, how much more precision we get with the EXPRES, which is needed to see, Earth-like planets. This is in meters per second, and so 60 meters per second is a very large signal. We're trying to do an order of magnitude better than that, and to do that, you need the much, much higher precision. The different colors just indicate different epochs that the observations were made for that. And so with that, I will finish up and take questions.
Yeah, thanks, Dave. We have time for a couple of questions, and we do have a couple. So first question came in from Travis Sawyer, who, this is sort of going back to the transiting question. Can other orbiting objects be mistaken for a transiting planet? In general, I would say no, because the other kinds of things that are going to cause a star to do like you see in the Kepler data with a decrease in brightness are actually something a lot of astronomers here at Lowell study, which are occultations. And those are going to be solar system objects and much more fleeting events than a planet making its way majestically across the disk of the star.
Right.
So that's pretty distinguishable.
So yeah, they don't have the periodicity.
Right. Yes, that too. Right.
Yeah.
And also a question from Lynn Sawyer. Hello, Lynn. Who's just asking how long did it take to produce this thing?
So yeah, believe it or not, it was from concept to installation was about a 3-year process, and that included the design and the fabrication and the commissioning.
Yep.
So very fast track and successful project, I would say.
And yeah, very much so. And especially given the performance, it's quite remarkable. Question from GKC Geoscience, that's Kent, hello. How long of an exposure do you need pointing to a given star?
Yeah, so this is getting a little bit into the science. There is an ideal exposure time. The important thing is the signal to noise. And so depending on the magnitude of the star, the length of the exposure would have to vary. And I think, for a very bright star, they might be minutes. For a faint star, it could be it could be longer, but you don't want it to be more than 20 minutes because of the correcting for the motions of the Earth in the solar system, which is called barycentric correction. Gets difficult to do if you go much longer than a 20-minute exposure, because during that exposure, things are moving, but you're not getting any measurement of that change.
Right. And that's very comparable. I'm really excited to have EXPRES here at Lowell because it's a very natural follow-on to the program I've been involved with here for 25 years, which is more studying the stars than the planets around the stars. So all the noise you're talking about in your program is kind of my signal, which makes EXPRES a very complementary kind of thing. But, we observed for 25 years with a much smaller telescope, only 1 meter of aperture, but also at much lower resolutions, only about 12,000 as opposed to 150,000. And yeah, typically on brighter stars, we would be going 1 to 5 minutes, but then on the fainter ones, you're up around 20 to 30 minutes. One question I had, Dave, we're going to see if we have any final questions here, but you've talked about this long, tortuous path that the light follows. So it comes through the telescope, goes through the front end module, you tilt it, then it goes through the fibers and you slice and dice it through fibers, and then it makes its way through the spectrograph. And of course, each one of those transitions, there's a little bit of light loss. And one of the important design elements in any spectrograph like ours or this one is you multiply all that together and you get a total efficiency. So, how much of the light ultimately makes it to the express detectors?
Yeah, good point. I don't know the exact numbers, but and it depends on the wavelength, obviously. But I think in the blue wavelength, it's like 6%, and in the brighter red wavelengths, it's upwards of 20%. And one of the difficult trade-offs with that is, of course, you want it to be as efficient as possible, but then you also want to cover as wide a wavelength range as possible. Mm-hmm. And so it becomes very difficult to do both because, for example, coatings that are used to make reflection of optics very efficient, are not real efficient when they're broadband. They have to be narrowband, but if you have broadband signal, you can't use those. And so there are a lot of trade-offs, and all of these went into the design of this instrument in order to get, the wavelength range, because the more lines you get, the more accurate you can measure the motion versus the throughput. And it's designed for a very specific range of planets that are known ahead of time. This was built for a project called the 100 Earths project. And these 100 stars that are known are being observed on a regular basis over a long period, a 5-year campaign, because one of the things I forgot to mention was an Earth-like planet like the Earth, it takes 1 year to go around the sun. And so in order to get a light curve, you have to observe it, or an accurate light curve, you have to observe it for at least a couple of years in order to determine that it's a 1-year orbit.
Right. Well, and of course, you've got it easy because those of us who study stellar activity cycles, that's 11 years for the solar cycle to complete. And, we find cycles ranging anywhere from 4 to 17 or 18 years. And really, that's one of the things that makes us very fortunate here at Lowell Observatory to have access to our own privately owned research facilities where we can just go out and do programs like this and observe 100 Earths and observe 100 suns and see all of these hidden patterns in nature that unfold only over long timescales. So if you're interested in this topic, you can find a number of other presentations here on the Lowell YouTube feed. I talked about our program for a while, and Joe Lama is on our feed talking about the solar telescope. So if this has been of interest to you, go ahead and look those up. Until then, I'm just going to say thank you very much, Dave, for giving us a little bit of a glimpse into how instruments are built. You can come back next week for interactive stargazing. Also, if the weather is nice, come back tonight for interactive stargazing. Always a fun thing where you can choose objects to be observed from the Geo Valley Open Deck Observatory, which is right here in my background. We're great to see that getting back into operation. Until then, as always, stay well, stay safe, and we'll see you next week.
Bye.